Good evening. Okay, let's not wait enough. We can start. Today we'll study about some important topic. This is also most important topic from this top chapter, that is heat engine. Heat engine. Now, as you know, what is heat engine? It converts. It converts what? Heat engine converts what? Energy into
Mechanical energy?
yes. Means mechanical energy in form like in you can say that as a work done. Mechanical energy we can say as work done. So this, if we take this as a hot reservoir and this as a cold reservoir. And this okay. So this is your hot reservoir. The temperature T1, cold reservoir T2, Q1 heat transfer, Q2 heat transfer. Now this Q1 is heat supplied. Now we saw before also, like when heat is supplied, some amount is given to the some amount is utilized as a internal energy and remaining is for what? Remaining for some amount is internal energy and remaining for
Mechanical energy?
uh, not yeah, it can, we can say mechanical energy, but in formula wise we can say as work done. It is mechanical energy only. So here we will say working substance. In form of work done. So W equals to Q total Q1 minus Q2. Total heat, this one. So what we did here, from hot reservoir, we are using that heat. So remaining is gone to cold reservoir, which is required, that is working substance. Some portion is used as working substance and remaining is sent back to cold reservoir. So it is a cycle. So let's find here efficiency. What do you mean by efficiency? Not like formula wise, but what do you mean by efficiency? Meaning,
Ability to do work properly?
how, or we can say how much.
Yeah, how much your ability?
Yes. like how much it can do the work as per the given input. Yes, very good. So finding ability or ratio of that, so we can do like this. Suppose like I'm giving some work here, or I'm doing some work, that is W, work done, and how much heat is given from the source. So heat taken from source, that is T1. So how much work is done and divided by heat taken from source T1. W Q1 minus Q2 divided by Q1. This will be Q1 minus Q2 divided by Q1. So we can say here 1 minus Q2 by Q1, or 1 minus T2 by T1, because here heat is from T1 and T2. I mean, yeah. So if you write this one for the first time, then remaining time we don't need to write. Just for first time, we will write here Q2. Where is Q2 here? It's from the substance. So this working substance is releasing remaining work, or sorry, remaining heat. So we will say heat released. Heat release, or let's write other way, amount of heat rejected per cycle to the sink T2. Q1, same way, amount of heat absorbed per cycle to source T1. Now, so if it let me ask you a question, but before that, done writing? We both done?
I took a screenshot, sir. You said this on the notes, right? After the chapter.
Yeah.
Even I took a screenshot.
Okay, fine. So what's the question here? Like, can this work done be greater than heat of a source T1? Can this be possible? Think, come on. Can this work done be greater than this? I mean, like, let's say like this. Numerator in this one, numerator can be greater than denominator. Yes or no? Not possible or possible?
It can be possible, I guess.
Okay. You guess so? Okay. What about Samhita? What do you think? Is it possible or not possible?
Sir, I think it's possible.
It's possible. Okay. So when we are thinking it is possible, let's go with that way. If numerator will be greater than denominator, means work done will be greater than heat given. So if we take numerator greater, so obviously the value of that will be greater than 1. That means efficiency. So efficiency greater than 1 means more than 100%. If the efficiency more than 100%, which is ideally impossible. So what is my next point here? Efficiency never greater than unity. Unity means 1. It can be 1 only in the case of, this is ideally 100% is also ideal. Only for like Carnot cycle. Even Carnot cycle is also not 100%. So we say ideal engine. Ideal engine. So practically, efficiency is less than 1. Okay? Refrigeration and heat pump. Now let's see, let's go back here. What was the source here? Hot reservoir. Sink. See, source and sink means here. This is your source. Sink. This is work. So here source was hot reservoir. So means from hot reservoir, we are taking the heat, we are utilizing that heat in form of work. Remaining is sent back to cold reservoir. Now, refrigerator work is reverse. Our cold reservoir will be the source. It will be working substance and work will be done. Then remaining will be hot reservoir. Heat will be taken from the system and given to hot reservoir. This is given in the system, and from that heat will be given from the system. So let's draw the same thing.
Sir, could you repeat that once?
Okay, in this one, in this heat engine, heat is given to the system. Okay, the system is our working substance, is our system for now. Consider this working substance as a system. So heat is given in the system. So work is done, whatever we required. Like example, like we want some iron box or something. Whatever, let's assume that as a heat engine. Actually, heat engine is something else, but just for small example. So if heat is given in that system, so we were using that system as a work done to iron our clothes or whatever. So remaining heat sent to the remaining portion is sent to the cold reservoir. Okay, there is our heat engine, convert heat engine into mechanical engine. It is not the iron box, but just for understanding work, I just gave example. In this refrigeration, what we need to release heat. We need to remove heat from the system. If we remove heat, then object will become cold, right? If I want to make something cold, what will I do? I'll remove the heat. Even your body also, when you are drinking water, you're already so hot. So what will happen? Your sweat pores will open, it will start sweating. So means it is releasing heat outside from the body. So same thing here. So let's draw and continue our discussion. This is cold. reserve, hot, reserve. This is working substance. So in this case, heat is given in the system, work done like this, and remaining is released to the system Q1. Let's take this as a Q2, Q1, T1, T2. Q1 minus Q2. So let's say where it went. Yeah. Let's write few points about it. What we can write here? A refrigerator or heat pump is a heat engine running in backward direction, means reverse direction. In this case, one thing is different, that is working substance. We use some CFC or chlorofluorocarbon as a gas, as substance. As a gas. That what it does? It takes heat from a cold body. Now, remaining heat will be given to this one, and this will be used as some other object or some other like a heat pump. We can use this as some other hotter body, external energy. We can use this. Colder body and gives out to a something, let's say, hotter body. External energy, that is electrical energy. So this both are, let me change color. This heat pump and refrigeration are almost same. See, in this one, we cannot find efficiency here. We need to find how much it can perform, performance. So here we'll have coefficient of performance. Of refrigerator or heat pump. So this is symbolized as beta. Heat extracted from coal reservoir work done on, it is on, right? Yeah. Work done on refrigerator. So which is Q2, Q1 minus Q2. Same way, T2, T1 minus T2. So T2 is temperature of cold body and T1 is temperature of hot body.
So is internal energy released here or absorbed?
Internal energy is utilized here. Like
Okay.
we can say this remaining is your like internal energy, which is remaining from the body. Like whatever it's given, same we did here. So it is given as Q1. So it's not actually internal energy here. We can assume that as a remaining portion because we studied in previous like first law, right? Heat is U plus W. So heat is in form of like internal energy and W. So we can assume that as an internal energy. Shall I scroll up? Chalo, I'll scroll up. We can go reversible cycle. Yeah, any other doubt here before going next? Are you okay with this heat engine and refrigeration? Yes, all of you?
Yes, sir.
Okay. What about others?
Yes, sir.
Mm-hmm. Okay. Madhusudan? No, from name itself we can understand. Reversible means which can be reversible. Which can go in reverse direction, means back. So we can say like a process which is going this way and coming back way or in opposite direction. Okay, so that is your reversible process. And which cannot go back, that is your irreversible. Simple. But there are some conditions. So that is what we need to concentrate. Let's see here. Understanding these definite words, okay. But now there are some conditions for it now. Let's see. Reversible process means which can in reverse direction, or let's say here opposite direction. Opposite direction, but in such a way a system, what we can say here, which can proceed in the opposite direction such a way that system needs that same process. System passes through same state. Same state and conditions. First thing, it should be very slow. Or let's take here extremely slow. No energy loss. In last one, you can say it should be in thermal equilibrium. Equilibrium means thermally. Thermal and chemical. With surrounding. So for this one example, can you give an example for this? This example, you know, daily you are using it. Come on, give me from your daily things you are doing. One example, come on. Aditi?
Water, sir. Water is
Yeah, water.
when it changes to gas or liquid, you can reverse it.
Yes. Yeah, vaporization, that means. Yes.
Any physical processes?
Yes. Any physical processes like fusion of ice. Okay. As you said, that's right here, vaporization. What's this? Vaporization. Is it right? Yeah, I guess, yeah. Vaporization of water. Then fusion of ice. Same way, if we go up, irreversible means opposite of this one. Irreversible process, which cannot trace back. In opposite direction. So which cannot be going back means other whichever like physical done, like a work done against friction. This cannot be reversed. Like loss of something magnetism, that is also not reversible. So those are irreversible. Almost all processes are irreversible. Almost all processes are irreversible, except few. These are easy things. Yeah. Come on, make a note of it. Then we can go for another important topic. That is second law, then entropy, Carnot cycle, all these things. Second law, entropy, Carnot cycle. Then our JEE question. So I hope today we can finish second law and Carnot cycles. So tomorrow we can do only JEE questions. Then day after tomorrow we'll start next chapter. Let's go. Is anyone writing?
No, sir.
Chalo. चलो तो फिर सेकेंड लॉ करेंगे. Let's write for statement, then we can have some discussion, longest discussion. It says that it is impossible for a self-acting machine unaided by external agency to transfer heat from one body at a lower temperature to body at higher temperature. Now, what it says, it is impossible for self-acting machine unaided by any external agency to transfer heat from a body which is at lower temperature to the body at a higher temperature. So generally heat transfer from higher body to lower body. Easily it can transfer hotter body to the colder body. But if you want to transfer heat from a body which is at lower temperature to the body at a higher temperature. So without any external support, it cannot be done. That is obvious thing. So we require some external support. For that, it should transfer from colder body to hotter body, as we saw in our, where is it? Pump. So in that case, our working system was the external source, which we are using. We are giving electrical energy so that colder body can go inside, means colder gas or whatever it is, heat can be removed from the object. So this system, it is used in your refrigeration. So what refrigeration will do, like it will keep your object, whatever, let's say example of water, keep your water cold. So for making it colder, so it should not get hot. So what will it will do? It will remove heat from that water. If you remove heat from the water, that will become colder. Now, if we keep giving a colder more, if we keep releasing more, then it will change to your ice, right? In like high temperature. Now that temperature will also act. But generally, when they're taking bottle from outside and keeping in the refrigerator, not deep freezer, but just refrigeration, then it will get colder. So for doing that, we are using one machine that is our refrigerator. That is worked by Mr. Electricity. So this guy is doing some work on this refrigeration. So it is going from colder body to hotter body. So we need some external agency to do this transfer. Without that, it is not possible. Next, in this one, we have to understand that is entropy. Can you down in this second law?
No, sir.
Okay. So let's understand entropy. So this most confusing term in this thermodynamics, just entropy. Let's make it, I'll give first statement, then you just will make it some, we'll say simple understanding as per my thinking. There is no exact like definition or something for that, but it's just a measure of disorder of molecular motion of system. See this one, what we wrote here, it is a measure, measure of disorder of molecular motion of a system. Now, in this one, disorder words is there, like you get so much confusion here. So let's make it simple words. Like how much, like we can say how much amount that energy which is used, which is no longer required as a work done. It cannot be done as work. We cannot like utilize it. So this disorder comes here, which is not required, which is amount of energy which is not available. Available to do work. Or not, available in the sense no longer available. No longer available, we can say. Over the, like, see, like simple way you can understand here, like, which is like yeah, here we can say. So amount of energy which is not available to do work, or we can say no longer available. Like when this time goes on, this energy is not there. This energy is already utilized, which is not, or not available. It is already utilized, or which is not available for the, like when time goes on, it's already done. It's already utilized. Like that, we can understand this. So in this one more thing we need to keep in mind, that see, more this disorder, there is advantage of this also. More this disorder, more the entropy. Greater the disorder, or greater the amount of energy no longer available, greater the entropy change. Entropy. So change in entropy as delta, excuse me, delta S is dq by T. Now dq is heat absorbed system and absolute temperature. So this one will be S final minus initial, something we can say like that, or initial minus final here. So we can say S1 minus S2 equals to dq by T integral part. So T is not in the integration, this is dq. There is no next class, right? I think so today. Not sure, let me check. Yeah, it's time is there. So this disorder, see, if I guess you might get confused with this disorder also. So let me think of another way. Oh yeah, simple way we can remember like this. Energy which is entering, it will increase disorder, and which is leaving will decrease disorder. Okay. I think this might be easy to understand. This statement makes easy. Yeah, are you able to understand now? Aditi, Samhita?
Yes, sir.
Yes, sir.
Okay. So if you just remember this point, it will be enough for that. Entering will increase disorder, releasing decrease the disorder.
So, but no energy is used during the reaction, right?
Energy is utilized, then only reaction will happen.
This is something about energy. Like, I didn't understand what you said. Okay, no longer. Okay, there's no energy available. Okay.
No available, no longer available to do that work.
It is utilized, but it's not available. After that, it's not available, right?
Yeah.
Okay. How do I do this?
What happened?
Nothing, sir.
Okay. Okay. I think this entropy took more time. I was thinking to do Carnot cycle also, but okay, we can do that tomorrow. Okay, girls, if you're done taking screenshot of that, I can stop here sharing.
So 1 minute.
Yeah, sure.
Done, sir.
Okay. Samhita, you?
Done, sir.
Chalo, ठीक है. Okay then, see you tomorrow. Bye-bye.
Bye, sir.